can we solve PDEs analytically just like we did with some ODEs? Well, there is some good news and there is some bad news. The bad news is that this is in general not possible and we need to resort to numerical solutions instead. The good news is that we can find solutions for some large and important classes of problems. Among the most important solution methods is the so-called separation of variables. In this video, you will learn all about this idea and we will use it together with concepts we developed before to find an analytical solution of the heat equation. So, what was the heat equation again? In the PDE, ut equals alpha squared uxx. We will impose now Dirichlet boundary conditions. We will set u to 0 at both boundaries. And there will be some initial condition f of x. And we don't specify it right now. It will be some given function f of x. Now the idea is as follows. We assume that we have functions un of x and t, which are functions which are the product of a function of x and a function of t. So we're looking for functions which are not just any function of x and t. No, they are product of a function which only depends on x times a function which only depends on t. We are looking for those functions un. And then we note that because we have a linear problem here, superposition of solutions will also be a solution. So our total solution will be then a superposition of this type of functions. So that is the ansatz behind the method. So what does this mean? So we say, okay, the un has to satisfy the PDE. They all satisfy the PDE. And the un have to satisfy the boundary condition. So what does that mean? At x equals 0, we have x of 0 t of t equals x of l t of t equals 0. So that means that both x of 0 and x of l have to be 0. And if we now take linear combinations, if we take a superposition, all our uns are 0 at 0 and l. So if we take linear combinations, those linear combinations will also be 0 at x equals 0 and x equals l. So our linear combination will also satisfy both the boundary conditions and the PDE. Now, then what about initial condition? Now, first we find the uns, then we take some linear combination of the uns, and then we choose the weights Cn such that we also satisfy the initial condition. So that is the set strategy. First find the uns, satisfy boundary conditions, then take linear combination and satisfy the initial condition. So let's take a look into more detail how this works. So we have this ansatz that we satisfy the PDE. X times tt equals alpha squared xx times t. There we substituted u equals x of x times t of t. Now we divide by x times t. Then we get tt over t. And here alpha squared xx over x. And now the important trick. T only depends on time and capital X only depends on x. So that means that the left hand side only depends on time. The right hand side only depends on x. But that's only possible if both sides neither depend on x and t. So that means that they are both a constant. So tt over t is a constant, neither depending on x and t. And xx over x is a constant, neither depending on x and t. And for convenience, we include in this constant the factor alpha squared. So we could just put a lambda on the right hand side as being a constant. However, it's convenient for use later on to call this constant alpha squared times lambda. So that is the idea of separation of variables. Because then we now have two ODEs instead of one PDE. We start with the ODE for the x. We have alpha squared xx over x equals alpha squared lambda, or xx over x equals lambda, or the following ODE over here with boundary conditions x equals 0, x0 equals 0, and x at l equals 0. But this is an eigenvalue problem. We have already seen before how to solve an eigenvalue problem like this. So I will give the solution immediately. So here there are some calculations. We will skip those calculations because there are videos before this one. And we will go straight to the solution. Solution is we have functions xl, which are of the form sine n pi x over L. You can verify, of course, if you plug in x equals 0 or L, that you are indeed at 0. And the lambdas are given by n pi over L squared with a minus sign. So we have solutions for multiple values of lambda parameterized by n can be 1, 2, 3, and so forth. Now, once we've found our x of x, once we have found our lambdas, we revert back to step A, because now we're going to look at the equations for t as a function of t. We have tt equals alpha squared times lambda. We have now found the lambda, so we can solve t n of t. That's just an exponential alpha squared lambda n times t. So there we have our function t of t. So now we multiply our x and our t, and then we have our function un. So we combine, and we have our un of x and t equals the x of x times the t of t. So, and our total solution is then a linear combination of un. So sum n from 1 to infinity, sum weights times the uns. So now we satisfy the PDE, and we satisfy the boundary condition, but we do not satisfy the initial condition yet. How are we going to do that? Well, for x at t equals 0, you plug in t equals 0 over here, then this whole exponential is just 1. So we're just left with the signs, is given by some f of x. F of x is specified. We only want to find the Cn. So how are we going to do that? For this, we use something else which we already developed before, the notion of a Fourier series. First we make the odd extension of f of x. Then we have an odd function, so we know we have a Fourier series of the following form. Bn sine n pi x over L. So the L should be inside the n pi x. Then we can compute the Bn's. They are integral 1 over L, integral minus L over L, this odd extension. Again, the L should be inside the sign. So we have our Bn's, and then we know that on 0L, f odd is the same as f. So if we want to express our f in terms of signs, we just have to use the same coefficients as the Bn's. So the Cn's we were looking for are simply the Fourier coefficients of our function f of x. So this is how we can compute our Cn's, our weights, and then we have our full solution of our heat equation. Well, in order to compute the Cn's explicitly, we need some explicit f of x. We will leave that to some later video, but over here you have the full procedure.